All right. So good morning, everybody. You might have noticed that there wasn't a video posted from last Friday at noon or 1:15 because no one called in. So does anyone have any questions? What date did I put down for our potential exam?
February 11th.
Okay, that sounds about right. Okay, so if no one has any questions, we're going to start doing some chapter 2 stuff. There is a lot of information there that you want to memorize because it'll make your life so much easier if you just memorize it. Plus, when I say memorize it, it's stuff that you're going to use for the rest of the semester. So if you don't learn it now, you'll be relearning it and relearning it and relearning it every week. And that's not a good idea. So let's go ahead and get started with some problems at the end of the chapter. And I'm going to change my share screen. And I'm going to put this thing in my way. Okay. So here we go. Define mass number. What is the difference between mass number and atomic mass? So I'm going to write these out. You need to know these. Atomic mass. Usually this refers to the mass in AMU of an average atom of an element. And mass number is the number of protons in the nucleus of that element. So if we take a look at carbon here, there's the number 6 at the top and 12.01. We have symbols for each of these. Actually, we have symbols for mass number, not for atomic mass. For mass number, the symbol is A. Don't ask me why. This is the, I'm sorry, mass number is A. This is called the atomic number. And this is the atomic weight. I usually call it the atomic weight, but it's also called the atomic mass. So you'll see I did not define atomic number above, but I wanted to point this out to you. Now, let's take a look at atomic number. Now, atomic number has the symbol Z. Okay, and this is the number of, and I got to change this definition. This is the number of protons. I'm a little slow today. Mass number, this is the number of protons and neutrons in the nucleus of that element. So make sure you correct that, protons and neutrons. And you can see that in the periodic table, there is no mention of how many protons and neutrons in the symbol, none. So you're not supposed to be able to figure that out from the symbol. So I'm going to collapse my window so I can only see who's talking and ask if anyone has any questions. Oh. Welcome, Jorge. You might want to turn your video off if you don't want to be recorded. Stop video. This session is being recorded. So, are we good on this one?
What is Z again?
Z is the atomic number.
Okay, thank you.
Okay, I'm looking for a few thumbs up, more than one, if we're ready to move on. We got a lot of stuff that we want to cover, so a lot of this you should have read about in hopefully the book. Okay, a gold atom has a radius of 145 picometers. If you could string gold atoms like beads on a thread, how many atoms would you need to have a necklace 36 centimeters long? So you can see this is a throwback to the previous chapter. I'm going to make a little drawing here. And we're going to make that 36 centimeters. And here's one gold atom, has a radius of 145. So I'm going to do this and put 290 dot nanometers because that's the diameter. So the diameter is 2 times the radius, which is 2 times 145 picometers. And I see we've got 290 picometers. Now you might be wondering, why does he have the decimal there? And the answer is that this formula is defined. So the 2 has infinity significant figures. The 145 has 3. So my answer should have 3 significant figures at least, if I don't want to round. But these would be zeros afterwards. So this is fine. Now, one of the things that we do know is that if we take a look at the number of atoms here, if you take the number of atoms times the diameter of one, that should equal the total length. I think that makes sense, right? The number of atoms times the diameter of one is the total length. The number of atoms is going to be total divided by the diameter of one. And we know that the total length is 36 centimeters. We know the diameter of one is 290 nanometers. And this is the perfect time to do that conversion I talked to you about, where you can actually substitute a number for the letter, because the letter is really a substitution for the number. So I can substitute 10 to the minus 2 for C because that's what C represents. And I can also substitute 10 to the minus 9 for nano. And when I look at this, I think 36 over 290 is almost 1/10, but a little bit more than 1/10, because 29 over 290 would be 1/10. 10 to the minus 9, when I bring it into the numerator, would be 10 to the positive 9. Add it to minus 2, and I have 10 to the positive 7 times 1/10. So that becomes 10 to the positive 6. So the answer should be probably, considering this is a little bit bigger than that, I figure the answer's got to be like 1.3 times 10 to the 6th. How many significant figures are we allowed? We have 3 here and 2 here, so we're allowed 2 significant figures. And we have an estimate of our answer. So I'm going to put 36 second EE negative 2 divided by 290 second EE negative 9. Okay, and I've got my answer. And I'm going to go ahead and put that in scientific notation. And now I'm going to wait for you to get your answer. And when I get a few thumbs up, I'll show you my answer if you tell me that you have your answer. You don't have to show me your answer, just tell me you got one. Let's see, we got 7 people in here, so I guess I'll go with 2 having the answer. I get 1.2 times 10 to the 6 atoms. Okay. Are we good to go here? Okay, excellent. Then let's go. Okay, give the complete symbol, including atomic number and mass number of a nickel atom with 31 neutrons. So we're going to learn about this. This is your standard isotope symbol. And I'm going to put X, A, Z. And I want to remind you that A is mass number and Z is atomic number. And X is the symbol of the element. It's either one uppercase letter or it's an uppercase followed by a lowercase letter. So that's this standard symbol, isotopes of an element. Let's write down the two important things about isotopes of an element. They have the same atomic number. And remember, atomic number is Z. So every atom of an element has the same number of protons in the nucleus. Secondly, isotopes of an element have different mass number, A. So that means a different number of neutrons in the nucleus. And in general, when you draw an atom, you draw the nucleus and you draw the region where you find electrons. And this is my symbol for electrons, E with a negative to it because electrons have a negative charge. The symbol for neutrons and protons are as follows. So if here's your nucleus, that's the symbol for a proton. That's the symbol for a neutron. Okay, so we've learned a little bit about these symbols and what they mean. We've got a nickel atom with 31 neutrons. So how do we figure out the mass number, which I want to remind you is the number of or atomic number, which is the number of protons in the nucleus, and how do we figure out its mass number? Well, you're going to need a periodic table to figure out the atomic number. And you'll always be given a periodic table on your test. So I'm going to put this off to the side here, and we're going to actually answer this. And I'm going to open up my periodic table, and I'm going to look for nickel, plutonium, and tungsten. So let's see here. Here's nickel, number 28. Here is tungsten, number 74. And here's plutonium, number 94. Okay. So tungsten has a really weird symbol. Probably this is named after the Greek name for tungsten. Tungsten, if you want to know what that is, it's back when light bulbs used to have filaments, they were tungsten filaments. Okay. So for A, B, and C, nickel has 28 protons. That's the number at top. So we put a 28 there. Now it has 31 neutrons. So 28 plus 31 is equal to 59. So it has 59 particles in the nucleus. And that's what we put at the top. Now I'm going to write that again. And I'm going to put a little arrow there. This is the number of nucleons. Now, nucleon is a word for a proton or a neutron. just like person is a name for a female or a male. So nucleons are found in the nucleus. That's why they're called nucleons. And they're protons and neutrons. And here you can see we have 59 nucleons. So therefore we have 59 protons and neutrons. This is protons. So all nickel atoms have 28 protons. And if we set this up like a subtraction, 1, 3, that would be the number of neutrons, because clearly the number of protons and neutrons should equal the number of nucleons. So let's look at plutonium, which has 94, I believe. So I want you to figure out the number that goes up here. And for tungsten, which is 74, I want you to figure out the number that goes up here. When I get a couple of responses, we'll move on. Remember, you're not telling me that you're willing to give me your answer. You're just telling me you're done. Okay, I get 144 up here, and that's 150 plus 94. Oh, not 144, 244. My apologies. Okay, and down here, I have 110 plus 74. So I'm going to get 184, and I get 184. And this is a particular isotope of nickel. This is a particular isotope of plutonium. And this is a particular isotope of tungsten. Are we ready to move on? We got 1, 2, that's good. We're good to go. Okay. Number 8 and 10 refer to the book. They must be a little bit long to write out. So let's take a look at that and see if we want to do them. Okay, so this is on page 107. And here is number 8. Let me zoom in on that a little bit for you. And we'll see if we want to do this one. The synthetic radioactive element technetium is used in many medical studies. Give the number of electrons, protons, and neutrons in an atom of technetium 99. We're going to do this one. Radioactive americium 241 is used in household smoke detectors and in bone mineral analysis. Give the number of electrons, protons, and neutrons in an atom of americium 241. So, number 8, A, we're going to be looking at technetium. $99. So I'm sorry you can't see that because I'm still zoomed in. And now you can. So we're going to be looking at technetium 99. And if we look in the book for this particular element, we're going to find it. Let's see, where is it? Boop, boop.
43.
Thank you. 43. So I'm going to draw this way, TC 43, and we have this 97.907. Okay, so here, what are they talking about when they are writing technetium 99? I'm sorry? So what are we talking about when we write technetium 99? We need to understand that. Okay, so what we're talking about with technetium 99 is this. So what does the 99 represent? That is the mass number. So the two ways we have of writing isotopes are the standard way, this way here, which is the standard way, and then there's the shorthand way. I don't really have a name for that way. I'm just going to call it shorthand. So you might ask, well, why would you do this? And the answer is that, 100 years ago, before we had computers, people were typing manuscripts for books, and this is a lot easier to do on a typewriter than this is. In addition, if you know what the symbol is, you can look at the periodic table and you can see the atomic number on the periodic table. It's right there. If you look at this 97.907, that's not 99. So you don't see the mass number on the periodic table usually. So that's why you give the symbol and you give the mass number. So we're going to write both of these out side by side so you can see precisely how they differ so that you know how to do that in the future. Now, also, you could write out the symbol's name and then 99. So I could put name A, and we could put tech netium 99. Now, chemists are usually going to do this or this. Personally, I like this one better because it gives you a little bit more information. And now with computers, we can do this very easily. Okay, does anyone have any questions about this particular problem and these symbols right here? Okay, so we're supposed to give the number of protons, the number of neutrons, and the number of electrons. Now, here's something that you need to understand about these three things is the following information. So I'm going to flip this page over so you can see what I'm about to write. These are called subatomic particles. And I gave this to you in the lecture, but I'm going to repeat it very quickly. Subatomic particles are particles in chemistry that are smaller than an atom that we're interested in. So there are smaller particles than what I'm about to give you, but mostly you're interested in those things if you're a physicist, not a chemist. So the subatomic particles we're interested in is the proton, the neutron, the electron. The symbol for each of these is P plus 1, N 0, and E minus 1. We'll find out what those numbers mean in just a bit. The symbol for a proton is also P 1 0. The neutron is N 1 0, and the electron is 0 negative 1. Now, in this case, when we look at the electron, negative 1 0, that's supposed to be the mass number, which is the number of protons and neutrons. And an electron is neither, so it's 0 protons and neutrons. Here, we learn that that is going to be the number of protons in the nucleus, but it also indicates charge. So that bottom number indicates two things, the charge and the number of protons. Clearly, you can't have a negative 1 proton, so this indicates charge. But if you take a look at this bottom number here, what's the charge in a neutron? 0. Oh, I messed that one up. That should be a 1. So I'm going to just cross that out altogether and put P11. So what is the charge in the nucleus of a proton? +1. Now let's write down some other things down. Charge. Protons are +1, neutrons are 0, electrons are -1. Mass in atomic mass units. Now I'm going to talk about the atomic mass unit for just a moment. The atomic mass unit is a relative mass. So that means everything relative to something. And we'll look at that mass in a little bit, but right now it's just a relative mass. So for instance, let's say that you have someone who weighs 100 pounds, and that is a relative mass, okay? So if someone weighs 100 pounds, we're gonna call that a relative mass of 1. So what if a person weighs 200 pounds? What do they weigh compared to that relative mass? They weigh 2 compared to that relative mass. So we could do the same thing. We could have the Tony unit. The Tony unit could be based on my mass. So we'll call that a 1. Now, I weigh 200 pounds. So if you weigh 100 pounds, you're half a TU. Now, this particular unit has not become popular because the problem with the TU is it keeps changing. So that's not quite what we want. All right. I wish it changed one way, but it's changing the other way.
Well,
So
then get outside.
what's that?
Well, then get outside. Move around.
Great. I'm being asked to stop the session and go for a walk. We'll see you all later.
Awesome. All right.
Okay. So here's what I want you to memorize for these, that for all practical purposes, use 1.00 for the relative mass of a proton. A neutron is 1.00. An electron is 0.00. What does that tell you about the mass of an electron compared to a neutron or proton? It's really tiny. In fact, it's really about 1/2000th the mass of a proton or a neutron. 1/2000th. Okay, so if we look at the actual mass, the mass in grams, this is a 1.67 times 10 to the minus 24 grams. This is 1.67 times 10 to the minus 24 grams. And this is a 9.4, I can't remember. I want to say 31 times 10 to the minus 28 grams. I wouldn't bother memorizing these numbers, but I would memorize those numbers. Capiche? I know it's going to be hard memorizing 1.00 and 0.00, but I'm going to ask you to do it anyways. Location. Nucleus, nucleus, surrounding the nucleus. I'll get my hand out of your way in just a moment. So these are some important aspects you want to know about protons, neutrons, and electrons. Plus, you want to know the following. We want to look at charge characteristics, charge characters. Okay, so there's a positive, plus there's negative, negative, okay? And you should know that opposites attract. So a positive charge would be attracted to a negative charge. And charges are additive. So let's say we have a particular atom that's got a proton in here, a neutron in here, and it's surrounded by 1 electron. What is the overall charge on this? Well, +1, this should be a 0. I don't know why I wrote a plus there. I think I'll cross that off and I'll put N0 like that. So +1 plus 0 is +1, plus a -1 is 0. So the overall charge is equal to 0. What happens if we take away that electron? Here, the charge is equal to +1. Charges are additive. What would happen if we had something like nickel? Nickel has 28 protons. What's the charge if you have 28 protons? Positive 28. Now, we are going to assume that unless we know otherwise, the atoms we're talking about are neutral. Neutral means no charge, or zero charge more specifically. So if we are talking about neutral atoms, how many protons are there relative to the number of electrons? And the answer is the same number. Okay, so we know enough information now to go back and answer number 8. We want the number of protons, the number of neutrons, and the number of electrons. So I'm going to go first here to this bottom number, 43 for the number of protons. That is the atomic number. Number of electrons is going to be the same. Number of neutrons is going to be the difference between these two values, 6, 5, so 56. So there's our answer to technetium 99. And there's a second half to this. B is americium. Americium is AM, and it's 241. What I want you to do is I want you to figure out the number of protons, neutrons, and electrons in technetium. When you're done, give me a little thumbs up.
Where are you?
So you have to find it on the periodic table. If you haven't found it yet, check the bottom row.
There you are.
Remember to give me some indication if you're done. I've gotten one indication so far. And there's a couple more. Okay, so 95 is what I found on my periodic table at the top. And the number at the bottom, we're not going to worry about because we don't need it. So 95 is the number of protons and the number of electrons. And so I'm going to rewrite this as 241.95, and I'm going to subtract. 1 minus 5 is 6 because I borrow 1 from that 4. 3 minus 9 is really 13 minus 9, which is 4. And then I have 146 for the number of neutrons. So there we go. Now, this is not a trick question. How much does that weigh in atomic mass units? How much does that weigh in atomic mass units?
241.
241. Now, in chemistry, we do a lot of abbreviations. These mean the same thing. This is atomic mass unit. This is atomic mass unit. This is an abbreviation for atomic mass unit. This is an abbreviation of an abbreviation. Okay. So we know it's 241 because we know that each proton and each neutron weighs 1.00. This is going to be good to 3 significant figures. Okay. We're going to move on to number 10. And let me zoom in on this so that you can read it. Move that over just a little bit. Okay, one of the things that you want to read about is what is a cathode ray tube? And a cathode ray tube is simply a device that shoots electrons. Now, this is called the anode because it attracts negatively charged particles. And this is called a cathode because it attracts positively charged particles. And we know opposites attract. So if the cathode is attracting positively charged particles, it's going to have a negative charge on it. And the anode, if it's attracting negatively charged particles, it's going to have a positive charge on it. Okay, so if you're shooting electrons from your cathode to your anode, what could happen is that one of those electrons could bump into an atom and knock an electron off of it. So imagine you have like a technetium atom with 43 protons and 43 electrons, and you knock an electron off of it. So now it only has 42 electrons. So if you have 42 electrons and 43 protons, you'll have a positive charge. So this is essentially how you're creating these ions. Ion just means the charged particle. You're knocking an electron off with another electron. And that seems doable, right? Knocking an electron off with another electron, especially if this other electron is going at a high velocity. That seems very possible. On the other hand, an electron knocking a proton off of an atom, remember electrons are 2,000 times less massive than protons. What's the likelihood of an electron knocking a proton out of an atom?
Unlikely.
Not going to happen. Not going to happen. And if it did happen, so if technetium went from 43 protons to 42, guess what? It wouldn't be technetium anymore. If you knocked a proton off of technetium, it'd be molybdenum instead of technetium. And that's not chemistry. Chemistry is not the nucleus changing. It's the electrons around the nucleus changing. So that's number 10. So what could possibly have knocked all those electrons and made a positive ion? Knock an electron off. Okay, so let's put that off to the side. We're done with number 10. Now, in the early, I'm sorry, I need to zoom out because I've zoomed in and I see that you can't read the question, but now you should be able to. I'm going to give you a moment to read this question. Okay, solid, massy, hard, impenetrable, movable particle. Sounds like a rock, doesn't it? So let's critique this description. So here's John Dalton's idea of an atom. It's like a rock. So that means that it's dense throughout, like a rock. How does that compare with our modern description? Well, our modern description is that you've got a nucleus, which is dense. It's where most of the mass of the atom is. And then you've got this electron region around it. And remember, if you only have one proton here, you've only got one electron here. And if you got 20 or 43 protons like technetium, you got 43 electrons around here. Now, this drawing that I have does disservice to the actual atom. So if I wanted to draw an actual atom, I would do something like this. This is where the electrons are found. And that's the nucleus right there. That's the nucleus. Now, if all of the mass is right here in that little dot and the electrons are floating around here, what is an atom? It's mostly space. And you might ask, well, let's say we have 43 electrons in this space. What's in between the electrons? Is it air? No. Electrons are smaller than air molecules. So what do we mean by mostly space? We mean nothing. Atoms are mostly nothing. And the nucleus is right there. To give you another idea of how big the nucleus is compared to where you find the electrons, think about a professional football stadium or baseball stadiums, something really big like that. And pretend that's your atom. So that's where you find the electrons floating around. How big would the nucleus be compared to a professional football stadium or baseball stadium? And the answer is about the size of a pea. That's the nucleus. So this is a ridiculous drawing. This is better, but it's kind of hard to draw something like that and say, hey, that's the nucleus and that's where you find all the mass. Okay, so how does this description compare to this? Totally different. So can you penetrate an atom? Turns out that yes, you can. You can take these alpha beams. So this is a symbol for alpha. Alpha particles are made out of 2 protons and 2 neutrons. And they have a positive 2 charge. They will go right through an atom unless they hit the nucleus, and then they'll bounce back. So atoms are mostly space, not hard, impenetrable, movable particles. Now, on the other hand, movable particles, sure, you can move atoms around. Solid, that's up to...
Debatable.
What's that?
Debatable.
It's debatable because, when you're talking about one atom, it's hard to tell if that's a solid atom or a liquid atom or a gas atom. So, that's kind of, I don't know, massy.
Yeah.
That's, again, debatable, Okay. Impenetrable. Well, certainly the nucleus is pretty impenetrable, but the rest of it is not. It is penetrable. Okay. So, any questions about Dalton's idea of the atom and what we know now?
So was that quickly dispelled by Curie and radioactive study?
No, it was dispelled by a guy named J.J. Thomson, who studied the atom, and he simply thought this. So this is J.J. Thomson. His name is spelled a number of different ways. Sometimes it's with a P, sometimes it's without a P. And what he did is he took gold foil.
Oh, yes.
And he shot these alpha particles at them. And his idea was that if these guys were massive, impenetrable, so this was the hypothesis, these particles would bounce off. Okay, so that's the hypothesis. In reality, here's what happened. And there was another model that said that atoms were more like plum pudding, which
Right.
doesn't mean impenetrable. And so here's the plum pudding model. These alpha particles would just go right through, like a bullet ripping through a piece of paper. Okay, so
Right.
these were the hypothesis. Now the reality is this. +99% of the particles went right through. Some of them bounced back, and some of them bounced off at angles. So if this is the detection screen right here, most of your particles landed right there, but they quickly found out that some particles were landing here and here, and they extended the screen around, and they found out that some particles were bouncing back. And they're like, how the heck do most of them go straight through and some bounce back? And the answer is, well, atoms are mostly space. That's why
Except the
most of us go
nucleus.
through, right?
Yeah, except the
One, some
nucleus.
And some bounce back because they're hitting the nucleus. Furthermore, because these have a +2 charge and they're getting bent a little bit, it may be that the nucleus has a positive charge that is repelling the alpha particles. And so that's why they kind of go off at an angle like this.
Cool.
And, we have this thing in science that says the simplest explanation is probably going to be correct. Not some, there's a magic hobbit inside of the atom that grabs the alpha particle, and depending on their mood, they let most of them go through, or sometimes they throw them back because it's an untasty alpha particle. When you think about that explanation, that sounds completely stupid. A more reasonable explanation is, hey, there's mostly nothing in an atom. Okay, so that's the Rutherford experiment. And the reason they use gold foil, of course, is that this guy here can cause a chemical reaction. What do we know about the reactivity of gold? Well, we know that it is very unreactive. It's so unreactive that we make jewelry out of it, and we expect that jewelry to stay the same for centuries. I mean, you go deep sea diving, not deep sea diving, it doesn't have to be deep sea diving. You go looking for sunken treasure for a boat that's sunk in 100 feet of water, and you find gold, you bring that up, scrape the barnacle off the gold, it looks like it was minted yesterday, because gold is highly unreactive. And that's why you use gold. But gold is also malleable, which means you can hammer it and get it to be really thin, because if the gold is too thick, all the particles will bounce back. And you want to make the sheet so thin that you can see through it. Okay, so that's the response to number 12. Let's move on. What is the mass of one O atom in grams? And the mass of an O atom is 15.995 U. So there's that abbreviation of the abbreviation. And for this, we're going to need to know what 1 AMU is. So I don't memorize it. I know it's 1.66, and I think it's 1, but I'm actually going to look it up because, again, I don't memorize it. And let me see what I can find here for the mass for 1 AMU. In the previous book, I knew where this was. In this book, I don't know.
It's 1 times 10 to the negative 24.
I want to actually get more significant figures here. Do you know what it is beyond 1.661?
No. No, but that's what you gave us in lecture.
Yes, but since we have the book, we're going to try and do a better job. And the reason we want to do a better job is if I use 1.661, I only get 4 zig figs. Here I've got 5. I've taken 5 zig figs and turned it into 4. That's not very cool. Okay. I'm almost there. Oh, there's naming. We're going to get into that in a bit. Okay. Here we go. It should be right here. 1.66054 times 10 to the minus 24 grams. So here we got 6 significant figures. So we're going to go 15.994 U times 1.66054 times 10 to the minus 24 grams per 1 U. So we can see that this number is going to be very small. 1.66 times this is like 16 plus 2/3 of 16, which is about 10. So we should get 26 times 10 to the minus 24, or 26 times 10 to the minus 23. So plug that into your calculators and see what you get. When you get something, let me know.
Tony, the problem has the last digit of the 15.99 is 5, and you rewrote 4.
Thank you.
Mm-hmm.
So I'll cross that out. That's a mistake, clearly, and I don't need to scribble it out. Uh-oh. So I said the answer should be about 226 times 10 to the minus 23. I made a mistake in putting my number in, but I'm going to continue as if I didn't make a mistake. Okay, and my answer comes out to be 7.45 blah, blah, blah times 10 to the minus 23. And I expected 2.6 times 10 to the minus 23. So I think I made a mistake. I think I made a mistake in my calculation.
Yeah.
So we're going to try this again. And I get 2.6560, 5 significant figures, times 10 to the minus 23 grams. And so this is the kind of work I would expect to see for a problem like this if it were asked on the test. Okay, any questions there? Are we good to go on? Yes or no? Actually, just give me a signal if you're ready to go on. Like a thumbs up or a okay, whatever. Okay, so let's move on then. Naturally occurring silver exists as two isotopes having mass numbers 107 and 109. So you need to know that silver has the symbol Ag. Okay. We have two isotopes with mass number 107 and 109. So I'm going to write silver 107 and silver 109. How many protons and neutrons and electrons are in each of these? So protons, neutrons, electrons, protons, neutrons, electrons. So what we're going to do is we're going to look this up on the periodic table, and we're going to find that silver is number 47. And interestingly enough, it has a number at the bottom that says 107.8682. I'm going to add one more part to this. I'm going to put mass here in U. So I want you to fill out these charts and give me a little thumbs up when you're done. Okay, we've got one. What the heck is that symbol? Is that an ice cream cone?
I think it's a little party horn or something.
Oh,
I got bored with the thumbs up.
okay. Well, we've got a couple of responses, so we're going to go ahead and go. The number of protons is 47. Number of electrons is 47. And that's for both isotopes. The number of neutrons here is going to be 107 minus 47. So 0, 60. So this has 60 neutrons, and clearly this has 2 more, so I'm just going to write 62. Now for a problem like this, I don't expect to see your addition subtraction stuff. I just expect to see the answers. Now the mass here is 107 AMU, and this is 109 AMU. Now we're going to do an additional thing. This is your mass of your average silver atom in AMUs, 107.8682. Now, if we know this one weighs 107 and this one weighs 109, if there were an equal number of silver 109s for silver 107s, what would the mass be? And the answer is the average of those two, 108. But the average mass is actually less than 108. It's 107.86. Why is that? Well, it turns out that there's more 107s than there are 109s. So if there's more 107s than 109s, the average mass is going to be lower than 108, and it'll be closer to 107 than it is to 109. So this number at the bottom is called the atomic weight or atomic mass. So the mass of an average atom based on how many there are of each isotope. All right, that wasn't asked here, but I wanted to try to give you an explanation for what that bottom number was. Okay, so we're moving along. Which of the following isotopes of element X, the atomic number for which is 9, so which is an isotope of element X that has atomic number 9? So for this one, very straightforward. We have to remember that the elements are written this way. And remember, the top number is the mass number, and the bottom number is the atomic number. And that's probably why mass number is given the symbol A and atomic number Z, is because if we're going to go A to Z, we want A on top and Z on the bottom. That's probably the reason they gave those symbols the way they are. You know, atomic number being Z instead of A is a little perplexing to me. So here, when we say the atomic number is 9, then this is an isotope of element X. This is an isotope of element X. And this is an isotope of element X. And this simply does not exist because you cannot have fewer nucleons than you do have protons. That's impossible. So I kind of like the way the symbols are written. We put the bigger number on top, the smaller number on the bottom, so that when you do a subtraction, it makes sense. And that's the number of neutrons. Are we okay to move on from there? Okay, we've got one response. I'm going to move on anyways. Strontium has 4 stable isotopes, blah, all reasonably abundant. Knowing that the atomic weight of strontium is 87.82, which of the more abundant isotopes predominates? Now, these are mass numbers at the top. 4 stable isotopes. Strontium 84 is very low. There's 86, 87, and 88. So I'm going to do a little line here, and I'm going to put 86, 87, and 88. So this is the mass of strontium 86. This is the mass of strontium 87. And this is the mass of strontium 88. Now, right here at 87.62, that's the average. So how is it possible, and then there's 84 way off here, but it's very small. How is it possible that the average mass of strontium is so large when there's these 3 isotopes? And the answer is strontium 88 is much greater in number than strontium 87 or strontium 86. So the number of these atoms is much greater than the number of these because the average is so close to it. It's kind of like asking, okay, just to exaggerate it, this is an elephant, this is a fox, and this is a mouse. And they're all isotopes of some sort of weird odd element, elephant, fox, and a mouse. If the average mass is close to that of an elephant, what do you have more of? Elephants, foxes, or mice? You got more elephants. Are you with me there, folks? Give me a little signal.
Yep. Ding.
Okay, excellent. Good. So moving along, verify that the atomic weight of magnesium is 24.31 given the following information. So you need to know how to calculate atomic weight if you're given the mass and if you're given the percent abundance. So here's the formula. the atomic weight, so that stands for atomic weight, is equal to the sum of the isotope mass times the percent abundance over 100. So this means sum of, not sum of. Okay? So let me show you what it looks like for this particular problem here. It looks like, I'm going to call that magnesium 24, and I'm going to write this out in great detail, not the kind of detail I expect to see on the exam, but the kind of detail so that you understand my solution. And I will put a block around what I would expect to see on the exam, okay? So I would expect to see this, that the atomic weight is the sum of the isotope times the percent abundance for that isotope over 100. I'd expect to see that formula because I'm always expecting to see the formula you're using to solve a problem, the general formula. In this case, I would then write, and this is not what I would write on the test, the mass of magnesium 24 times the percent abundance of magnesium 24 over 100 plus, and here's that sum of part coming into play, the mass of 25 magnesium, or magnesium 25, times the percent abundance of magnesium 25. And again, I'm only doing this so that you can easily follow my solution hereafter, times the mass of magnesium 26 times the percent abundance of 26 magnesium over 100. And that's what we're going to do here. This next part I would expect to see 23.985042U times 78.99 over 100. Now, you guys remember that I told you whenever you use a percentage, you should put it as that number over 100. And that's what I expect to see. Now, with percentages, the top unit and the bottom unit are identical, so we don't need to put the units here because whatever unit we put on top, we put the same one on the bottom and they cancel. So then I would expect to see 24.985837U times 10.00 over 100. And then plus 2598, 2593U times 11.01 over 100. So I would expect to see this on your exam and this on your exam. And then I would expect to see the answer. So let's go ahead and do this work. And I'm going to show you how to carry significant figures through this, okay? So we have 23.985042. I think I did that right. Times 78.99 and then divided by 100. Now, clearly, my number should come back to be less than 23.98. And since this is about 80% of this, I expect my number to be about, well, let's see, about 19 or 18, okay? So here, get 18.94578,468U. Now, how many significant figures am I allowed in this number if I were to round right now? And the answer is, I got a whole bunch here, but I only have 4 there. So I would round to that place right there. Now this one I can actually do in my head. It's going to be 2.4985837U. And I have 4 significant figures, so that's good too, that 8 right there. This one I know is going to be close to 2.598, but a little bit more. So it might be 2.6 something. Let's see what we get. So I get 2.86068U, and this is good also to 4 significant figures. So I wouldn't expect to see this work. But can everyone see that we're now doing addition and we're not doing multiplication? So for significant figures, we're going to round based on precision. This is precise to 2 places over from the decimal. This is precise to 3 places over. This is precise to 3 places over. So which one is less precise? This one here. So I'm going to round to 2 places over from the decimal. So I'm going to add these numbers all together. And as long as I wrote these numbers down correctly, I should be okay. And I made a mistake clearly because I'm looking at my calculator and I get 30.75. Do these 3 numbers add up to 30? That's
No.
19. That's 2.5, which makes it what? 21.5 plus 3, which makes it like 24.5. No, I made a mistake, so I got to put all these numbers in again. I don't know what I did. Okay, and I get 24.30U. So the things that I boxed off are what I would expect to see for the solution to this problem. Any questions here?
I have a question.
Yes.
Do we need to write out the individual sums for each isotope like you did?
Oh, just what's in the box.
Okay, so we can just plug it all into our calculator as one long thing.
Yeah. Can you see how you can go from here to here very easily without doing all of this?
Yeah.
Now, why did I do all of this? So that you can see that that is the mass of 24. That is the percent abundance of 24. I just did this so you could see how this gets populated. That's all. Now, the number is actually 24.31, I believe, in the book. But this is this reasonable compared to the book?
Mm-hmm.
Yeah. And actually, I think the book has 24.305 or something like that. Let me check. Yeah, 3050. So you can see that this is really close to what the book has. Okay. So normally on the exam, I ask a question like this. So here's what you're going to do to practice this is you're going to go ahead and give this one a shot without looking at your notes to see if you can do it and set it up. That's the best way to get good at these things is practice, practice, practice. Okay, moving along. Take a look at this one. Can you see how we're doing this again? Only this says calculate the percent abundances of these isotopes. So we have 2 table isotopes. We want the percent abundance. how do we do that? Well, this is a tricky one. Let me show you how you do it. So to show your work here, you would do something along the lines of this, that the atomic weight is equal to the sum of the isotope mass times the percent abundance over 100. That's how we're going to start. Now, this says two stable isotopes. They're not saying to calculate the atomic weight because they're assuming you can look it up. So in our book, europium, it's in that bottom two rows. It has an atomic weight of 151.964 U. That's the atomic weight. And this is going to equal isotope mass 150.9197 U times, I'm going to call this X, plus 152.9212 U, and I'm going to call this Y. Okay. Now, if we take a look at this mass here, 151.94, that's really close to 152. This is really close to 151, and this is really close to 153. Since this is a little closer to 151 than it is to 153, I think maybe there might be a little bit more 151. Okay, that's a guess, but it's so hard to tell because of these numbers aren't precisely 153. All right, so let's move on. How do we solve a single equation with two different variables? And the answer is you can't. You can't. Okay, so you need two independent equations to solve something like this. Here's your other equation you're going to use. X plus Y. Remember, X is the fractional abundance. The percent abundances add up to 100. What do the fractional abundances add up to? They add up to 1. So that means Y is equal to 1 minus X. And then now we have 151.964 U is equal to 150.9197 U times X plus 152.9212 U times 1 minus X. And you solve for X. Now, from here on out, it's just algebra. So I'm going to let you do that algebra work and go from there. Now, first thing I'd do is I'd say U cancels out of each of these, so I don't need those anymore. And I might actually write this out as the atomic weight is equal to the mass of isotope 1 times X plus the mass of isotope 2 times 1 minus X. So the atomic weight is the mass of 1 times X plus the mass of 2 minus the mass of 2 times X. Then the atomic weight minus the mass of, atomic weight minus the mass of 2 is equal to the mass of 1 times X minus the mass of 2 times X. And that becomes atomic weight minus the mass of 2 is equal to X times the mass of 1 minus the mass of 2. So that means X is equal to the atomic weight minus the mass of 2 over the mass of 1 plus, minus the mass of 2.
Oh boy.
So if you take a look here, all I have to do is plug numbers in here and I'm good to go.
Yeah, it's just hard to follow when your hands on it. I can hear you, but
Well, the Cool thing about this is you can always go back and watch the video and pause it.
Yeah, I know. It's just more time. It's good.
Yep. Well, if
Yep.
you're not doing 17
do
hours
it.
a week, you're not doing enough.
No, I'm doing it.
Okay. So this would be how you would go about doing this particular problem.
Okay.
There is another way to do it, but this is the way I expect you to do it on an exam.
Mm-hmm.
Okay, and when I say this is the way I expect you to do it, I expect to see this. I expect to see this. I expect to see this. And then I expect to see that X is equal to, so let's say we get X is equal to 51.02, actually, I'm sorry, 0.5102. The actual question is calculate the percent abundance. So to get the percent abundance, it's the fractional abundance times 100%. So in this case, we would get 0.5102 times 100%, which is 51.02. And then the percent abundance of the other one, I would do it this way. So we'll call this 1. Percent abundance of 2 would be 100% minus 51.02%, which would be 48.98%. Because these two numbers should add up to 100%. So I'd expect to see, once you get that number there, okay, we're going to call it quits here on this one. And I'm going to tell you that tomorrow you're going to do a mass spectrometry lab where we're going to be doing stuff online. It's best to actually show up to me talking about the mass spectrometry lab, but I will record it. And you can do it without even looking at the study session tomorrow. But it's kind of a neat exercise. And the whole idea is to get you thinking about mass spectrometry, thinking about what happens in mass spectrometry, making predictions based on what you know about mass spectrometry, and testing those predictions. And if you get your prediction correct, great. If you get your prediction not all the way correct, great. The important part is not getting it right, but analyzing what you had done and trying to improve so that when you do the experiment again, you make better predictions, okay? Ultimately, you may never make the correct prediction, but as long as there are parts of your prediction that are correct, that's called science. Most scientists don't get every part of their hypothesis correct. Something is a little off kilter, and we learn from that, and then we do another experiment. That's the natural course of science, not to get it correct the very first time and hit the ball out of the park. That rarely happens. In addition, if that does happen, it doesn't count. You guys did the reading, hopefully. You find out that, oh, okay, you have to be able to repeat the experiment. A one and done is not done in science. It's got to be like 100 and done. And not only do you want the same person to be able to repeat their experiment, but you want Joe Schmo in some other town or Jill Schmill in some other town to be able to repeat the experiment and get similar results. When you have all sorts of different people doing the same experiment and getting similar results, then you go, aha, this is something we start to believe. You don't just trust one person doing it one time. And there are some experiments where it's very hard to repeat. And so in those cases, what you do is you have a lot of peers who are steeped in that particular area, experts, look at the data, look at the interpretation, say, yeah, this is good to go. Or no, they're hanging their butt out on a limb. No good. So, so there, I'm not sure where I got off on all that, but it's important to know. Okay, I want to thank you all for attending today. I appreciate the audience. I hope you learned a little bit here. And tomorrow will be mass spectrometry. I'll be posting that tonight sometime. It's a lot of online type stuff, and I can guide you through it if you show up a lot easier than you reading it on your own, although you should be able to read it on your own and hopefully figure it out. Okay, so mic's on and say adios.
Adios.
Sayonara.
Adios.
Bye.
Sayonara. All right. Thank you for attending.